Hello, and welcome to the TI Precision Lab that introduces the concept of effective noise bandwidth in a signal chain. In this module, we will discuss what effective noise bandwidth is, where it comes from in your system, and how to calculate and simulate the combined frequency response and noise density of multistage filters. In a subsequent presentation on effective noise bandwidth, we will analyze a delta sigma ADC's digital filter frequency response and its combined effect with a first-order low-pass filter to better understand how to calculate total system noise. The goal for these effective noise bandwidth Precision Labs modules will be to apply the knowledge from these examples to help determine the total noise in your next signal chain design. To begin, let's revisit the simple data acquisition system used as the basis for the analysis throughout the ADC noise presentations. We previously made the claim that these three components, the ADC, amplifier, and voltage reference, generally contribute the most noise in your signal chain. In order to calculate the total noise of this system, you would take the root sum square of each component's individual noise contribution using the equation shown here. But how do you calculate the amount of noise each component contributes? Can you just read noise values directly from each component's datasheet? Unfortunately, this is not always possible. Sometimes noise is given over a specific frequency range, such as 0.1 to 10 Hz, which may not cover your system's requirements. Or as shown in the amplifier noise equation at the bottom of the screen, noise can be specified as a spectral density instead of an RMS or peak-to-peak value. Noise spectral density generalizes the relationship between noise power and frequency and has the units of noise per root hertz. Therefore, you need to know the system bandwidth in order to calculate the amplifier's noise contribution in this example. However, the amount of noise filtering applied to each component is often different, as multiple filtering stages combine to act on an individual component. Moreover, the input signal and reference input paths can behave differently, depending on the filtering applied. In either case, you must calculate an effective noise bandwidth for each component in the signal path to determine its noise contribution. As stated on the previous slide, the focus of this presentation will be on understanding the concept of noise bandwidth and how filters combine to act on one or more noise sources in your system. Therefore, you will not need a detailed understanding of ADC, amplifier, or voltage reference noise to continue. However, you can view the Precision Labs modules on these topics if you want to learn more. Let's now quickly review what effective noise bandwidth is. Effective noise bandwidth is a mathematical approximation that helps simplify the calculations that determine how much noise each component passes into the signal chain. The effective noise bandwidth of any component or system is the cutoff frequency of an ideal Brickwall filter whose noise power is approximately equivalent to the noise power of the original filter. The Brickwall approximation accounts for non-ideal filters allowing frequencies beyond the cutoff pass into the rest of the system. Using this method provides a much more accurate result when calculating the total amount of noise that is able to pass through the filter. For example, the 40 Hz low-pass filter shown on the left side of this slide has an effective noise bandwidth of 63 Hz, as shown in the plot on the right. The scaling factor of 1.57 is an approximation for determining a first-order low-pass filter's effective bandwidth from its cutoff frequency. For more information about how this scaling factor is derived, as well as calculating the cutoff frequency for different filter types, please review the Precision Labs modules on amplifier noise. Let's now take these principles and apply them to an entire system. Here is a more complete view of a typical analog signal chain showing two distinct input paths. Each stage in these paths has some definable bandwidth that acts as a filter. The signal chain filter path can include the bandwidth of the sensor being measured, the cutoff of any electromagnetic interference filters, the bandwidth of any amplifiers in the signal chain, the cutoff frequency of the anti-aliasing filter, and finally, any digital filters integrated into an ADC. The second input path is from the voltage reference, which also has some definable bandwidth and generally includes a low-pass filter at the output to limit how much voltage reference noise enters the system. A buffer might also be included to ensure proper settling and ADC performance for higher speed data acquisition. Not all filter types need to be included in every data acquisition system. For example, both wideband and low-speed delta sigma ADCs integrate a digital filter as part of their conversion architecture, whereas SAR converters typically do not. Additionally, all of these components contribute some noise to the circuit as well as help filter noise from previous stages. As a result, it is possible that the ADC noise will have a different noise bandwidth compared to the amplifier, for example. So how can you determine the effective noise bandwidth seen by each component in both the signal and reference paths shown here? And how does this help you calculate the noise performance of your system? To answer these questions, it is necessary to understand how to combine different filtering sources using frequency response plots. Shown here are two arbitrary frequency response plots for filter A in red and filter B in blue. Filter A could represent the EMI filter shown on the previous slide, while filter B could represent the anti-aliasing filter, for example. To determine the cumulative effect of both filters, you can combine them by adding their decibel responses point by point. The purple plot on the right side of the screen represents this combined response. Note that the combined response looks like filter A until approximately 10 kHz, where it begins to roll off at -40 dB per decade. Also note that while only simple first-order low-pass filters are shown here, combining filters of any type can be completed using this technique, assuming that each plot is expressed in decibels. Moreover, this technique can be applied to more than two filters. Also, since you are adding point by point, the position of filter A compared to filter B does not matter. If filter B was actually the EMI filter and filter A was the anti-aliasing filter shown in the signal chain on the previous slide, filtering seen by a noise source prior to the EMI filter would still be represented by the combined response shown here. This result is important as it allows you to approximate your system's effective bandwidth given various filter types, regardless of the position of those filters in your signal chain. We will explore some of these approximations on the next slide. In general, you can approximate the combined frequency response of two or more filters as just the cutoff, Fc, in the order N of the filter with the lower cutoff frequency. These approximations are valid when there is a difference of greater than or equal to 1 decade between the filter cutoff frequencies, as the systems on this slide show. For example, the top row of plots show that filter A in red has a cutoff frequency, FCA, of 1 kHz in an order NA equal to 1, while filter B in blue has a cutoff of 100 kHz, FCB, in an order NB equal to 2. Using the point-by-point addition method introduced on the previous slide, the combined frequency response in purple is very similar to just filter A's frequency response in terms of both cutoff frequency and filter order. You may note that the combined frequency response is affected by filter B, though this does not occur until a gain of -40 dB and a frequency of 100 kHz. From a noise perspective, this means that filter A has attenuated the bulk of the noise power before filter B starts to affect the circuit, so using filter A as an approximation for the total response is acceptable. Also, due to the transitive property of combining filter responses discussed on the previous slide, if filter B came before filter A in your signal chain, the combined response and the resulting approximation would be the same. Moreover, if filter B had a much lower cutoff compared to filter A, the approximation still holds true, though filter B's cutoff frequency and filter order would dominate in this case. However, if this condition is not satisfied and the two filters had similar cutoff frequencies, you can no longer apply the approximations. Instead, you must add the frequency responses of all filters and use the resulting combined plot to apply to your noise source. This is shown in the bottom row of plots, where filter A has a cutoff of 1 kHz and NA equals 1, while filter B has a cutoff of 1.1 kHz and NB equals 2. The resulting plot has a cutoff frequency that is approximately equal to 1 kHz, with an effective filter roll-off of -60 dB per decade. This much steeper roll-off means that n total is equal to 3, or just the sum of both filter orders. Now that you understand when and why these approximations are valid, as well as how to calculate the noise bandwidth of a low-pass filter, let's apply these principles to a design example. Shown here are 3 arbitrary filter responses and 3 arbitrary noise sources. These components could represent any part of the typical signal chain discussed earlier in this presentation, such as the EMI filter, the gain amplifier, and the anti-aliasing filter. Additionally, each noise source has a noise spectral density that represents real components used later in the simulation portion of this module. Similar to the example at the beginning of this presentation, determine the total noise of this system by taking the root sum of squares of each stage's noise. To calculate the noise of each stage, you multiply the given noise spectral density by the square root of the system bandwidth seen by each source as shown. You can use the principle of superposition as well as the techniques presented throughout this module to calculate the combined filter response seen by each source and the resulting bandwidth to calculate total noise. To begin, let's look at the frequency response seen by each source. On the top portion of this slide, noise source A sees all of the downstream filters, so you must calculate the combined response by adding each filter point by point. However, note that filter A's cutoff frequency is at least 1 decade lower compared to either filter B or filter C, so you can approximate the combined frequency response as just filter A's cutoff frequency in order. In this case, a first-order low-pass filter with a cutoff frequency of 1 kHz. Since filter A is a first-order low-pass filter, you can use the effective noise bandwidth equation shown at the beginning of this presentation to determine the bandwidth for the system. As shown, this bandwidth is calculated to be 1.57 kHz. Plugging this bandwidth value into noise source A's equation yields an RMS voltage of 0.4 microvolts. In the middle, noise source B sees the response from multiple filters just like noise source A. In this case, filter B and filter C. Also similar to the analysis for noise source A, noise source B has one filter that dominates the combined frequency response, though this time it is filter C. Since filter B's cutoff frequency is an order of magnitude greater than filter C's, you can approximate the frequency response seen by noise source B as just filter C, a first-order low-pass filter with a cutoff frequency of 10 kHz. Applying the same bandwidth approximation for a first-order low-pass filter used for noise source A, the bandwidth seen by noise source B is 15.7 kHz. This results in an RMS noise voltage of 0.63 microvolts. Finally, on the bottom of the slide, noise source C is very straightforward since it only sees the frequency response from filter C. You can therefore use the 15.7 kHz bandwidth derived for filter B to determine that noise source C adds an RMS voltage noise of 0.38 microvolts to the system. Now that you have determined the noise of each component, you can apply the root sum of squares to calculate the total noise. Shown here is the original system used in this example with the voltage noise of each source identified. Taking the root sum of squares of the voltage noise for each component, the total voltage noise of this system is equal to 0.84 microvolts RMS. However, you might wonder how this compares to a simulated example using actual component values. Several assumptions were made regarding the filter order and bandwidth of each stage to reach the results shown on the slide, which begs the question, how close are these approximations to the actual system noise? The schematic shown here is a real-world implementation of the filter system on the previous slide. Filter A and filter C are simple first-order low-pass filters comprised of a resistor and a capacitor. Filter B is a second-order low-pass Butterworth filter designed using Texas Instruments' online filter design tool. You can access this tool to create your own filters at the link on the screen. An ideal amplifier was chosen for filter B in lieu of using a real amplifier to keep the noise analysis simple. This choice will be explained in more detail on the next slide. The switches at the output of the voltage source, as well as the switches between the filters, enable simulation of the entire system, as well as each individual component. For example, to determine the voltage noise density for just filter C, you would close switch 3 only. These switches are only included to make the analysis simpler and would not need to be included in a real design. Now, let's analyze the simulated results. This slide shows 6 plots to confirm the performance of each filter. Note that for all the plots shown here, switches 1 through 3 on the schematic were closed, while switches 4 and 5 were left open. This enables each filter to be analyzed separately to determine their individual characteristics. On the left, the 3 frequency response plots confirm the cutoff frequency in order for each filter. The figures on the right plot the noise spectral density for each filter. Note that the chosen component values yield noise spectral densities that match those used in the theoretical example. As stated on the previous slide, an ideal op-amp was chosen for the second order filter because a real amplifier would add complexity to this system. You can see on the yellow plot on the top right that there is already a slight increase in noise spectral density around the cutoff frequency, even when using the ideal op-amp. This discrepancy results from impedance in the feedback path, causing a noise gain, not a signal gain, that would be exacerbated by a real amplifier. In a real-world application, it would be necessary to account for these variables, but for the purposes of understanding the concepts in this module, it can be ignored. Now that we have confirmed that the simulated filter parameters match the theoretical example, let's look at the performance of the combined system and compare it to the calculated results. Here are the key plots for the simulation of the combined filter system. The frequency response plot on the left shows a system cutoff of 937 Hz, while the voltage noise plot on the right shows 0.82 microvolts of RMS voltage noise. Comparatively, the theoretical model predicted a filter cutoff of 1 kHz and 0.84 microvolts of RMS voltage noise, so the assumptions about which filter dominates in a multi-stage filter system proved to be valid with an error of only 20 nanovolts. This small discrepancy between the theoretical calculations and the simulated data results from the assumption that the system frequency response would depend solely on the filter with the lowest cutoff frequency. In reality, this was not completely accurate, such that the downstream filters actually did affect the cutoff frequency. Moreover, the shape of the frequency response curve suggests that approximating the combined filter as first order was inaccurate. You can see that the combined filter starts to roll off at negative 40 dB per decade at negative 50 dB of gain, and at negative 80 dB per decade at a gain of negative 120 dB, representing a fourth order system. So how is it possible that there is such a small error between the predicted and simulated noise if the combined response is so dissimilar from the simple first-order low-pass filter? In fact, you can see this issue more clearly by overlaying the first-order response from filter A on the combined response, as shown in the plot on the left. Fortunately, this apparent issue actually results from the way these curves are displayed, not the behavior of these filters. Specifically, the logarithmic y-axis on the plot on the left exacerbates the difference between these two curves, making them seem more dissimilar than they actually are. If you were to use a linear y-axis instead, you would get the plot on the right. Note how the combined response and filter A by itself look almost identical using a linear y-axis. Importantly, note that the vast majority of the noise power has been attenuated by 10 kHz in either case. This means the downstream filters have little to no effect on the overall response, even though the combined filter order changes from first to second to fourth. Ultimately, these results prove that you can use the frequency response approximations and methods employed in this presentation to quickly and confidently analyze the noise of your next signal chain. You are also prepared to use simulation techniques to confirm the validity of these hand calculations, as well as account for any non-idealities similar to the ones seen with the second-order low-pass active filter. Check out the next video in this series to understand how to calculate the effective noise bandwidth for the digital filter commonly found in Delta Sigma ADCs. This filter type presents a unique challenge that must be understood in order to calculate the total noise of a system using a Delta Sigma ADC. That concludes this video. Thank you for watching. Please try the quiz to check your understanding of this video's content. Question 1. For the circuit below, what is the effective cutoff frequency seen by the signal source ENA to the output Vout? The correct answer is A, 1 kHz. When several filters are cascaded, the cutoff frequency will be equal to the cutoff of the lowest filter. Question 2. Combining filter stages A, B, and C below form a 1 kHz filter. What is the order of this filter? The correct answer is A, first order. When several filters are cascaded and the cutoff frequencies are significantly different, the order of the lowest cutoff filter will dominate. In this case, the qualifier significantly different means the cutoff frequencies are apart by more than 1 decade. Question 3. The two circuits below are identical except that the position of filter A and filter B are swapped. Which circuit will have the lowest total noise? Note that both noise sources are included in the analysis. The correct answer is C. Option 2 is better. If you look at option 1, you will notice that the 7 nanovolts per root hertz source is followed by a 1 megahertz filter. On the other hand, option 2 follows the 7 nanovolts per root hertz source with a 1 kilohertz filter. Option 1 will allow more noise to reach the output, so option 2 is better. Note that from the perspective of the input 1 nanovolt per root hertz noise source, the filter sequence doesn't matter, so both options are equivalent from the input noise source perspective. Question 4. For the circuit below, what is the effective cutoff frequency seen by signal source ENA to the output Vout? The correct answer is C, 10 kHz. The general rule is that when the cutoff frequencies of two cascaded filters are the same, the cutoff frequency stays the same. In reality, the cutoff will shift to a slightly lower frequency, but there is no simple equation to predict the frequency. Typically, this result is sufficient for a good rough estimate, and a more precise result can be calculated using SPICE. Question 5. Combining filter stages A and B below form a 10 kHz filter. What is the order of this filter? Correct answer is C, third order. The general rule here is that if two cascaded filters have approximately the same frequency, the orders will add. Since the cutoff for these filters are both the same, the orders will add. So the first order plus the second order yields a third order filter. Question 6. Find the total integrated noise for the circuit below. Include the effects of both noise sources. The correct answer is D, 1.26 microvolts RMS. The calculations for this problem are shown on the right. From filter A perspective, the combined filter is a first-order 1 kHz filter. Using this information, the total noise at the output from the 2 nanovolts per root hertz source is 0.079 nanovolts RMS. The 1 nanovolt per root hertz noise source sees a 1 megahertz filter. The output noise of this source is 1.25 microvolts RMS. Combining both output noise values using the root sum of the squares gives about 1.26 microvolts RMS.